Debalay Chakrabarti from Indian Institute of Technology, and let me put it below. Yeah, somewhere. So the austenite and ferrite grain size variation in microalloyed steel. Some of my industrial partners are there from India, and Dr. Dave Crowther from Vanitech, who has been a very kind supporter of our work. So we acknowledge him and the work funding received from Vanitech. So what happens is, if there is such a coarse grain size in between the fine grains, this kind of mixed grain structure is often found in structural and line pipe steels, particularly which contain elements like niobium and also to certain extent titanium. These can be very detrimental for properties. You may find in literature this kind of very coarse grains, presence of very coarse grain in between fine grains have been reported. And sometimes you will find that there are very coarse particles also. So if this kind of coarse grain and coarse particles are present, say titanium nitride or niobium titanium carbonitride, then we know that this can be very detrimental for impact toughness point of view. So primarily we are focusing on structural and line pipe grades of steels. So coming to the next slide, that what we have done is we have first of all, let me give a brief introduction of our institute. It's situated at the eastern part of the state called West Bengal, near the ocean here. So it's called Kharagpur, and the institute is established in 1951, and some of our eminent alumnus from our department, Lord Kumar Bhattacharya, who has set up the Warwick Manufacturing Group in UK, Mr. Sundar Pichai, Mr. Arun Sareen. So there were several students passed out from this our academic institute. It's we have BTech, MTech, and PhD program. So coming to the third slide, we have actually either received industrial grades or manufactured several grades from the steel plant pilot scale. So the grades at the top are, you will find all these grades are containing all three elements: niobium, titanium, as well as vanadium to certain extents. And later on, the grades that we have made are primarily only vanadium grades. So here you can see that we have varied the vanadium and nitrogen concentration, because nitrogen is also considered to play a very important role in vanadium steel. But the top grades, cast 1, 2, 3, 4, are all niobium, titanium containing steels with some amount of vanadium and nitrogen as well. So what we have found that this is the ASCA structure, which is a typical dendritic kind of microstructure. You can see that these are the secondary dendritic arms and the dendrite propagated in this direction. And this is the typical cast structure, the microstructure of continuous cast slabs of say 290 mm thickness, in the order of say 250 to 90 mm continuous cast slab thickness. So what we have noticed is, when we looked into higher resolution microscopy, that at certain locations there are an enrichment of precipitates and inclusions, that if you see quite a wide region we are seeing, and in this middle part there are small dots like precipitates. All these white spots are precipitates, and these black features are inclusions like manganese sulfide and titanium nitride with manganese sulfide and alumina and all those things. So what it is trying to say is, in this part there is an enrichment of elements which led to higher density of precipitates as well as inclusions. But away, we have found several other locations where precipitates are much less in density. So it shows that the precipitate distribution is inhomogeneous. It's not an uniform precipitate distribution in as cast slab. Now let us have a more closer look into these precipitates. You will find these are often a dendritic type of precipitates, and sometimes spherical and sometimes cuboidal precipitates. And these are glowing because this is the second, this is the backscatter electron image, where these precipitates are enriched with niobium primarily, with some titanium. And because of higher atomic number, they are actually appearing bright on the dark, relatively darker matrix. And if you see even closer look into the precipitates, you find different morphology, different shape of the precipitates, and they contain niobium and titanium. So you may see also in the ASCA steel, there are some array kind of precipitates. All these are from precipitate rich regions where precipitate density is very high. These, as I said, the precipitates along with titanium nitride and other particles. Even we have found titanium precipitate to distribute in an inhomogeneous fashion within a small location. So many titanium nitrides are there. At the slab center, we have even found very coarse kind of features. These are titanium rich. If you see EDS, titanium rich with lower niobium, and these are niobium rich with small amount of titanium. So these are quite coarse. And if you see the slab center, these kind of very large particles of niobium precipitates segregates, and sometimes eutectic of niobium carbide or niobium carbonitride have been found. And these kind of things have been reported quite a long time. If you see the work of Prisner and co-authors, if the segregation of niobium is very high, then it can create this kind of network, grain boundary network, particularly at slab center, but also at quarter thickness and other location. So these can be quite coarse if you see 30 micron size. So these also are brittle and can be detrimental for properties. Here we are showing laser ablation study with plasma mass spectroscopy. So we are trying to show the distribution of niobium as an element in the cast structure. And here is the distribution. You see the cast structure and the niobium distribution is quite following the structure, and it's an inhomogeneous distribution. At the interdendritic region, niobium actually tend to segregate. And if there is a 0.5 niobium level, it tends to segregate between say 0.8 to 0.9 in the interdendritic region, and much less at the dendrite center region. So basically, due to segregation, the elements get partitioned with a higher amount in solute rich interdendritic part and lower amount at solute depleted dendritic part. And these kind of things can be predicted also. This is simple thermocalc prediction. During solidification, as the temperature decreases, we see niobium in the last liquid can enrich up to 7 times as per thermocalc prediction. Whereas in titanium, it can enrich up to 5 times of its average composition. Whereas elements like vanadium, 1.8 maximum, aluminium, even less. So these elements, particularly say vanadium, is much less prone to segregation. Niobium is most prone among the microalloy elements, followed by titanium, and vanadium is the least. And further calculations you may find in our publications, just thermocalc may not be fully reliable because of its assumptions involved. So we have gone for other models like Klein-Kurtz models and things, and we have predicted the compositional variation in a much better way. I will come to these things in the later slide. So the story is, what happens is when these ASCA slabs were reheated to different temperatures, say 1000 degree, 1100 degree, or 1150 degree. This one is 1150, sorry for this mistake, and this is 1200 or 1250. What we have found in this temperature range, 1150 to 1200, there is a grain size variation, and these are austenite grains. These are austenite grain boundaries revealed by picric acid etching. So very coarse grain along with very fine grain. We do not see this kind of variation at lower reheating temperature or soaking temperatures and higher soaking temperature. So you see the how clearly this austenite grain size variation can be observed, that we see here very fine grain, and very coarse grain. And the distance between these two fine grain regions are about 250 micron, which is same as the secondary dendritic arm spacing. So what we are trying to say is, what happens that during solidification, there can be microsegregation or interdendritic segregation. And because of that, in regions like this, there are a lot of precipitates, niobium precipitates. And because the local concentration is also high, those precipitates also remain stable. And as a result, at an intermediate reheating temperature, they can strongly pin down the grain boundaries and the grains becomes much smaller. Whereas at this location, dendrite center location, the solute concentration is much less. So the precipitate fraction or density is less, and those precipitates are also less stable. As a result, when we heat up to this kind of a temperature, those precipitates dissolve completely at this region and the grains can grow into large size. So this creates a mixed grain structure. This doesn't happen at lower temperature because precipitates remain more or less everywhere. to some extent. The extent may vary, but precipitates are there everywhere. Even if we hit to a higher temperature, say 1250 or something, then precipitates dissolve mostly from all the locations, and we tend to get a more uniform and coarse grain structure. But in the intermediate temperature range, in the range of say 1100 to 1200, we must be very careful, at that can create a mixed grain structure. And here we are showing those precipitates are pinning the austenite grain boundaries. They are lying at the austenite grain boundaries, niobium precipitates. Here, titanium precipitates are pinning the grain boundaries. And if you see here that what we are trying to say is there are interdendritic region where there are solute enrichment and their grains are pinned, so fine grain, whereas in dendrite center region, grains can grow freely. Coming to the next slide, you see, I want to show you more detail. See, if we look into the precipitate at this fine grain region, reheated structure, you see here so many precipitates, all these white dots are precipitates. Whereas if we see precipitate from this region, the coarse grain region, precipitates are almost completely dissolved. So this proves the hypothesis that precipitates are more stable and more in number in interdendritic region compared to dendrite center region, and that is caused by segregation of elements. So what we are trying to say is, if there is a segregation, then almost the material is divided into two different portions. One is solute rich portion, and in the solute rich portion, suppose if this is the prediction of thermocalc prediction of niobium precipitate fraction and stability, solute rich region, interdendritic region, you will see the precipitate fraction and stability will be much higher. On the other hand, this is red hollow squares at niobium, same precipitates at the solute depleted or solute poor region. So there the precipitate fraction is less, stability is less. So what happens is, if we reheat, and the temperature is here in Kelvin, so if we reheat in this domain, say in between somewhere here, what we tend to see is niobium precipitates are present at interdendritic region where they dissolve completely at dendritic region, and we tend to get a mixed grain structure. Titanium nitride particles are mostly more stable, and they may not contribute so much to grain size variation. On the other hand, vanadium precipitates are much less stable, and vanadium also segregates much less. As a result, we see that vanadium precipitates do not contribute to grain size variation. They basically do not pin the grain boundaries at typical soaking temperature range. So you see in, in a higher resolution image, I am showing that these are the grain boundaries, prior austenite grain boundaries. It's a martensite microstructure. The samples are quenched and etched in picric acid solution. So the grain boundaries can be revealed, and on the grain boundaries, the precipitates are primarily present. So these precipitates are pinning the boundaries. This is the proof. So the model that we are schematically presenting is, in the interdendritic region, there are a lot of precipitates, and the precipitates are also more stable. Dendrite center precipitates are less stable, and precipitates fraction is less. Sorry. And here, when we reheat, the precipitates will remain more stable in the interdendritic region, and in the dendrite center region, they tend to dissolve. And as a result, when the austenite grain forms during soaking, you see a fine grain in this region and coarse grain in this region. But when we have studied vanadium steel, what we have found is vanadium steel, only vanadium with higher nitrogen or less nitrogen, with sometime aluminum, that this kind of grain size variation is hardly noticed. The grains are coarser than niobium containing steels, but irrespective of the reheating temperature, whether it's a low soaking temperature, intermediate or high soaking temperature, there is not a significant grain size variation. And this can be dealt with, because we know that if grains are uniform but coarse, then if we apply heavy roughing deformation, the grains can be refined. But if the grain size variation is there, then it is always expected to remain to certain extent. So that is the problem, what can happen in niobium steels if we are not careful. So here we are showing grain size distribution for some of the steels. This is the niobium steel also containing vanadium. At intermediate temperature, you see 1150, the grain size distribution is almost bimodal, completely bimodal, two separate modes of the distribution. In low and high temperature, fine and coarse, but unimodal. In vanadium steel, we have found the grains can be quite coarse. Its maximum size going up to 400 micron, but the grain size distribution remains unimodal. because as I showed that vanadium does not segregate to that much. So it whatever happens, it happens uniformly. If it remains, it remains. If it dissolves, everywhere it's the same. That's why these elements do not contribute to grain size variation much at soaking temperature. And one more thing I would like to come, niobium is an element, even if suppose we dissolve the precipitates, but segregation is expected to remain because the diffusion is not that fast for this kind of elements, substitutional solute elements. And we know if we simply look into the effect of microalloying content on the recrystallization stop temperature, niobium, you see the blue curve is niobium. So niobium has a much stronger effect on the recrystallization stop temperature, whereas titanium and vanadium has a least effect. So what we are trying to say is if niobium is there at high amount, even in solution at some region, there the local TNR temperature will be higher, much higher. If the niobium is low at certain location, the local TNR temperature will be much lower. So if we deform at the intermediate temperature, there is a risk of grain size variation by partial recrystallization, because we know that we should not roll a steel at the partial recrystallization region. And if there is segregation, this partial recrystallization temperature band increases because this temperature becomes much higher at niobium rich region, whereas it is much lower at niobium depleted region. So we need to be careful, and there can be ways of predicting that. We know that if we consider uniform composition everywhere, then there will be certain precipitation recrystallization interaction as per Datta-Siller's model. But if there is a variation in composition, then there can be different curves, one separate curves for precipitate solute rich region, one separate curve for solute depleted region, with both regions having different recrystallization stop temperature. But this risk is much less in vanadium steel because vanadium is not prone to segregation, and it also doesn't influence the TNR temperature to that extent. Its role is primarily precipitation during transformation. And you see that when we have deformed at an intermediate temperature range, austenite grain size showed partial recrystallization, whereas it's expected to show complete recrystallization if we deform above TNR. So ultimately, if these things can happen, also you see if there is a segregation, then it can influence the transformation temperature. The AR3 temperature can be different at solute rich region and solute depleted region. So overall, all these factors can lead to grain size variation. And this grain size variation is not good because say when we are doing Charpy testing, we know that there is a stress and strain intensification in front of the notch. And if there is a coarse particle, and segregation can also increase the particle size because the local solute concentration will be high. So particles will also be large. So if there is locally a large particle or a large grain or combined presence of large particle inside a large grain, then this is very detrimental and it can cause catastrophic brittle fracture. So some of the cases, if you see that impact tested samples, when we have gone back and found the origin, cleavage origin, we found that very coarse facets are present, which possibly have come from the coarse grains. And sometimes it contains titanium nitride, niobium precipitates, or in this case, manganese sulfide. So the point is the presence of this kind of coarse grain at the notch root can be very bad because that can cause premature fracture at lower temperature. And sometimes examples we are showing that titanium nitride particles are causing crack. So I'm skipping this slide. So overall, what I tried to say, I have covered. One more thing is how much time do we need to completely homogenize niobium? You see, niobium is strongly prone to segregation. Its homogenization takes 30 hours of soaking at 1200 degrees. So complete homogenization is not possible because we cannot afford to keep a slab for 30 hours. Or even more. Its partition ratio at least decreases to 1, even 30 hours of soaking. On the other hand, vanadium, its initial partition ratio is less, 1.2 or something. And after a less time, after 3 hours of soaking at 1200, it is expected to show. So this is the vanadium curve. So here is the solute rich regions and here is the solute depleted region. So this calculation is for manganese, niobium, titanium, vanadium, and carbon. And we know carbon homogenizes very fast because it's a interstitial solute. Its diffusion is very fast. But these elements, niobium, manganese, titanium, vanadium, their diffusion is relatively slower. So it's better if the initial segregation is less, as in vanadium, the homogenization happens much easier. So it takes much less time for homogenization. So in these publications of ours, you may see some of the results are reported. And presently we are doing this work on vanadium microalloyed steel and grain size uniformity in vanadium steel and their effect on properties. So with this, I think I have come to the end. So these are our students who do the research and that we can present. So thank you for the opportunity. And I also thank the funding agencies in India and also Vanitech for supporting our research. Thank you very much.